So let me start saying a big thank you for inviting me tonight. I'm very happy to be here and to talk about the work that I recently started, actually, but it's an exciting new mission. So I'm very happy to share, what we are doing at NASA these days. So let me first start to talk about quickly who I am. Let me see if I can. Does it go? Let me see. Should I do this? Okay, perfect. So you may hear an accent in my English. That's because I'm Italian and I moved here 10 years ago and I've been working in NASA since 2017, basically. So I am an astronomer. I did astrophysics and astronomy back in Italy, and I came here as a researcher. And I've been doing ground-based and space-based astronomy across the solar system. So I've been studying, for example, comets and the atmosphere of comets. I've been studying Mars atmosphere, and I've been studying, for example, the plumes of Enceladus and ocean worlds. So I'm trying to investigate the chemical composition across the solar system of many objects that have an atmosphere. Anything that has a gas and atmosphere, it's something that I would like to, investigate and work on. And so basically that's me, and it's brought me into working with space telescopes as well, like for example the James Webb and now the HWO, the Habitable World Observatory. And so talking about astronomy, one of the first questions that we can ask to ourselves is why do we need to launch telescopes in space when we do have telescopes on the ground? That is one of the first questions probably people ask themselves. Why do we always have to send new telescopes? Well, the answer to this question is very simple. Because we do have a very thick atmosphere on our planet that it's absorbing a lot of the wavelength of the light. So when we do want to do astronomy, we want to study the object in the sky, and we want to study either the light that this object emit, for example, star, that they emit lights, or we want to study the light that this object reflect or they absorb and they re-emit. And so to do that, we need to be able to catch those lights at all the wavelength range. So from the very short wavelength and very energetic one of the gamma, X-ray, and ultraviolet into the long wavelength and less energetic one, like the radio, for example. And so as you can see here, depending on the wavelength, so depending on we can say colors of the light, not all of them can reach the ground. So we can have telescopes that can, for example, look at the visible or some windows in the infrared, and catch a lot of the radio wavelengths, so this part of the light, but not all of them can reach the ground. And so this is one of the reasons we want to go to space, but also because despite you look at the sky and it seems very clear and kind of empty, it is not. It's composed by many molecules, and those molecules absorb part of the light. And there is also what we say pockets of air that can be warm or cold, but what they do is basically they sort of disturb this light coming into the atmosphere, and basically it's what we see the stars twinkle, for example. So we have these pockets of light, pockets of warm and cold air that basically don't allow to have a very sharp image of the object that we want to study. And so despite we have good software and good technology to correct for all these things, going into space will certainly remove all the issue that we can say our own atmosphere basically produce into astronomy. And so you can see here a different observatory, but what I wanted to show to you are this one. Why this one? These three observatories are part of actually a couple of dozen observatories that are in space right now. So there are like probably 20 to 30 observatory telescopes. But I select these three because they're part of the NASA Great Observatory plan. Basically, this is 30 years of exploration that has been going on. And these three, observatory has been cornerstone of this, great observatory program. And so why these three? Well, because these three select different wavelengths of light. And as I told you before, wavelengths of light are interesting because you can explore different energy regimes, different physical phenomena. And so, for example, here we can see that if you want to study the Crab Nebula, and you would study that with the Hubble Space Telescope or Chandra Space Telescope or the Spitzer, which is now, unfortunately, it's not anymore, there. It's been replaced by James Webb, of course. But if you want to explore one object within different wavelength ranges, you can learn different energetic and physical phenomena about the same object. And so you can put everything together and have this broader view, broader picture about all these processes that are going on. And so you can see, for example, Chandra can, with the X-rays of very energetic and very short wavelength, tell us all about these very high energetic phenomena. And you can see in the infrared with Spitzer, we can see something that goes beyond the dust, and so all these warm and emissions. And so the beauty and the strength of doing this is that we can combine and we can do contemporaneous observation, and we can overlap the operation of this telescope to have a better understanding of the universe and the sky. And of course, since Spitzer is not anymore available, the next one that I wanted to show you is the James Webb and the Romans, because those two are going to be this current decade telescopes, because the James Webb has been launched in 2021, is currently working wonderfully. Actually, it just completed the first 5 years of mission successfully, I would say. It is an infrared telescope. It has this wonderful honeycomb 6 feet actually, 6 meter probably, yeah, meter feet is never easy for European to remember. But anyway, a very this large primary mirror that it's able to capture a lot of light and has advanced and cryogenic wonderful instrumentation that allow us to do so many incredible things, not just in the universe with galaxies and stars, but also in our own solar system. So many discoveries with this new telescope that we just had, for the last 5 years in space. And actually, you can see here on the right a picture that I just took today in Building 29 in NASA, where the Roman Space Telescope was facing the window where people can go and look at the status inside the white, big white cleaning room. And you can see here people working and refining the last things before, shipping the telescope to Kennedy Center for the launch that probably is going to happen this September. So this is actually one of the recent picture, actually from three hours ago, of the Roman Space Telescope, which is going to be, the next one launching. And it's going to be also very important because it's going to have a very huge field of view. So it's going to have this capability of mapping the sky that was never done before, much broader than Hubble. And it's going to have a very important technology demonstration that is going to then, help the development for the HWO observatory, so the Habitable World Observatory. So this is going to be a pioneer in this sense telescope, because it's going to have these instruments that I'm going to talk about it later, but it's a coronagrapher that is going to help us identify planets around other stars. And so, having this idea of all these telescopes in space, let me introduce this next big telescope that NASA is going to build just right after we launch the Roman Space Telescope, and it's going to be the Habitable World Observatory. And you can see here a first idea of the architecture. Clearly, people are already starting working on different architecture, different concept. This is just one example. But it's going to be a very huge telescope again. It's going to have a big mirror, bigger than James Webb, honeycomb again, and it's going to work into the UV and visible and kind of part of the near infrared. And this is going to be a sort of a huge super Hubble. Think about that. And so the primary objective of this telescope will be to take images and identify potentially at least 20 to 25 Earth-like planets around other stars in the universe. And so why we want to do that? Because what we're trying to answer, as usual, one of the main questions that the astronomers and astrophysicists scientists have, is trying to understand, are we alone in this universe? And so, this is one of the main driver. And so we need a powerful observatory and powerful new technology to be able to answer this huge question. And so do we have any hope to find habitable Earth-like planets? And so let's do a little bit of understanding and math. So let's say we have, in this picture here, you can see the Hubble Deep Field. Is one of the many beautiful deep field, picture has been, done by Hubble, but this took like hundreds of hours and is 300-ish exposure, separate exposure, all combined together. And so think about it, something like the Roman Space Telescope will provide something like this pretty quickly. It's going to take like probably an hour instead of hundreds. And so in just this picture, that is going to be only 1/24th of the entire night sky, we have basically 3,000 distant galaxies. And we know that, a galaxy contains billions, millions of stars. Okay, and so if you think about, that you have all these galaxies, and then you can see all these stars into these galaxies, and this is just 1/24th of the entire night sky. And you can think that at least you may have one or two planets, they may be habitable around the stars. You add everything up and you discover that you may have 1 to 2 trillions of exoplanets alone, and probably you can find, something like 10 to the 22 number of exoplanets around the whole night sky that you can actually try to characterize. So it's huge. And are we alone? Well, probably not. Probably there is something else, some sort of life in the universe, and we want to try to identify it and observe and characterize. But clearly, we know life the way we know life, life based on water, and we know life based on a life that is available on a planet that is in a habitable zone. What does it mean? It means in a zone around this host star where water is liquid. That's our definition of having life, having liquid water and having all the ingredients of life available, and having a good temperature that is not too hot, having a good surface temperature that is not too hot or too cold, having an atmosphere with a good molecule for life, the life that we know, of course. And so all these requirements define something like an habitable zone and something like habitability. So something that could be habitable by the life that as we know it, of course. And so why a new telescope, the Habitable World Telescope, is necessary? Because there are two problems that we need to solve to get into identified and then characterize Earth-like exoplanets around other stars. The first problem is that we're trying to see the light and identify, like, think about a firefly flying around a very bright searchlight torch. It's gonna be almost impossible, and you're gonna have to see that firefly flying around that torch from like thousands of miles away. So it is a very tough problem. That's called the contrast problem. So trying to identify Earth-like planet, which is 10 billion times fainter than the star is around. And you need to do that you need to establish and develop a very stable and advanced technology. And so right now, there are technology, and there is, for example, coronagraph, which is basically, let's say camera, let's say, and it has a little disc, and the little disc is basically put on top of the star, and the starlight is blocked, and you can see the planets around. So that is the basic concept of a coronagraph. But in order to do that, we need to have a very, very stable star blocking system technology that allows us to see these very faint, billion times fainter planet around the star. And so, as I said, the Roman Space Telescope is gonna bring now in space a first demonstration technology. And then what we're gonna do with this telescope is gonna develop these very, very high new technology in order to identify these planets. But clearly, our planet has been evolving. So if you look at our planet today, it's very different than our planet in the past. So you can see here in the left, the different abundances of one of the main, let's say, main molecules that are important for life. And so we have water, of course, we have oxygen, that is a bioproduct and we need, to breathe. We have carbon dioxide, we have methane, and we have ozone. And so you can see here with different color in the plot on the left that these abundances of this material change during the billions of years of evolution of our own planet. And so if we look at our own planet today, which is the plot on the right, and it's a spectra where basically we show all the molecules that absorb the light, and we see the wavelengths, so at different, colors of light, how those molecules are. And so basically, they behave sort of a fingerprint. So if you see the specific absorption at the specific wavelength, it is that specific molecule. And so we can identify with this technique of spectroscopy the composition of planets, for example, or objects in general. And so if you look at our own planet today, this is how it looks like, and it has these fingerprints. It has methane, it has water, it has oxygen, it has ozone. But if you go back in time, you would see that this is very different. And these are the four molecules that we wanted to, of course, focus for life, because methane can be produced also by methanogen, which are a sort of bacteria that produce methane as product. And so it's important for search for habitability, not to search just for life as water-based life, but also methane as a product of a possible different organogram, And so you have, in the past, Earth was very different. You have the Proterozoic era, where ozone, for example, was not as abundant as is today. And we had much more, for example, oxygen goes down, ozone, it was much more not like today. And then we have basically that the carbon dioxide, it's pretty much similar. And then we have, going back in time, in the Archean Earth times, we have that basically we don't have any more ozone at all. We have a drop in oxygen, and what it's dominating the atmosphere is methane and carbon dioxide. And you can see here that you can have these spectral feature, we say, so these sort of fingerprints that can tell you whether you even have a clear atmosphere or a planet with a lot of dust and hazes, for example. But it was a methane dominated and CO2 dominated atmosphere. And so it was very different. And so what we want to do with this telescope is try to identify Earth-like planets around different stars, but at all these stages of evolution of our planet, and see also when, a planet like Earth could be, inhabited, or how and if it will become habitable. And so this telescope will be revolutionary in this sense to search for these sort of Earth-like planets. And so since we do have telescope now in space, one of the questions could be, well, how is it going to be revolutionary? Can Hubble do anything? Can James Webb do any of these? We have Roman with this demonstration technology. Can Roman do any of this? And so, well, if we look at Hubble has 2.4 meter primary mirror, so a very small mirror basically. And you need a huge collective area, meaning that if you want to collect a very, very faint light from those very, very far planets, you need to have a very big mirror. And so, yes, James Webb has already a 6.5 meter mirror. And so Habitable World is supposed to have between 8 to 10 meter mirror. So think about, you want to collect a lot of water. If your bucket is bigger, you're going to collect more water than it's smaller, right? So you need to have this big mirror to collect a lot of photons. But not only that, because Hubble is in an orbit that it's close to our own planet, around 500 kilometer close to Earth, while telescopes like James Webb and then HWO in the future will be at L2, Lagrange 2, which is at 1.5, I believe, millions kilometer distance from Earth. And so it's very far, and meaning that it can catch a different, portion availability of the sky, and it's going to be in a position where it doesn't have a lot of straight light and contamination of light, and it's going to be able to have a very, very crisp and detailed image of the sky. So this is going to be something compared to Hubble. So it's going to have this much bigger mirror in a different location. It's going to have better resolution, of course, and more powerful instrumentation. Okay, but so what about beyond James Webb? Because James Webb is big, it's powerful, and it's in L2 in the same location. Well, James Webb can do exoplanetary research. Indeed, James Webb has been working, discovering a lot of exoplanets, and many, many papers came out. But the strength of James Webb in the near infrared, so what I was telling you, in a different wavelength regime, is about detecting light from this exoplanet in a specific, we say, technique that is called transit. So it means that you have to wait for the planet to go around the stars, and basically you catch the light through the star light, and so you then remove the starlight, and then you get the exoplanet light and spectra. And so the problem with this is that transit are rare, because you have to be very lucky that your planet is passing in front of the star, so you have to have a good alignment with that. And is a different also wavelength regime. So if you want to study habitable planet, you want to get into those wavelength of the UV and then the optical, where you can catch all those molecules that I showed you earlier, like for Earth, for example. And so what HWO will do is have this new technique of blocking lights and image Earth-like planets. Because right now, what we can do with the coronagraph that we have, it's image up to Jupiter-like planets, so very big planets, which are further out. But what we want to do is get closer, get into the habitable zone, and image these very nice, faint, small, pale blue dots, I would say, Earth-like planets. And so that is something that is going to be, a leap relative to James Webb. And relative to Roman, let's talk about Roman, because Roman is going to be launched in September, and it's going to have this coronagraph technology, which will be a tech demo, we say. So it's something that we've been sending now in space to proof of concept and demonstration. And the difference between the classic coronagraph, where you have this disk that you cover the star, It's going to be that you want to image that planet and it's basically immersed in the starlight, and you just don't have a disk that it's covering your star, but what you have is a combination of these different masks and shape shifting mirror and disk. And what happens is that you have a distracting light interferometric. And basically what happens is that the light of the star disappears, and what you have is that you have the light of the planet appearing. So it's a very, very sophisticated technology. But again, we expect to get, let's say, 1 to 100 million, maybe 1 billion fainter planets. It's what we were talking before, the contrast problem. And what we wanted to get with HWO is getting to 1 to 10 billion fainter planets relative to the star. So the contrast has to be, much bigger. So we wanted to get these very faint planets. And once we image those and we can identify those, then we can do spectroscopy and we can characterize the composition of those. And so with this technology, this telescope has a lot of science driver, not just, finding habitable world, which is the primary goal of this new telescope, but also a lot of transformative astrophysics. And for example, trying to understand the dark matters from the movement of the stars around the edge of the galaxies, or for example, trying to understand how many black holes are in the Milky Way from the rotation and non-Keplernian rotation of these stars around, in something that it's empty, in the space. Or for example, we want to characterize our own backyard, the solar system, because we discovered that despite we can send space mission to some of the planets, and we have a lot of space mission on Mars. We are now having space mission going to Europa, and we're planning to go into the farther solar system. We've been already visiting the solar system in the farther out. But space mission go, they provide you incredible information, but then they're gone. You wanted to keep monitoring those planets because they change, they evolve, they have season. And so I'm excited for this telescope, as I was excited for James Webb, and I am excited for James Webb, is to study our own backyard, to study the solar system. And so here you can see a composition of planets, and you can see real images from James Webb, for example, Jupiter here, beautiful with the auroras. You can see Uranus and Neptune and the beautiful ring system and all the moons. And then you can see Mars and Venus, which are not accessible right now with James Webb, because James Webb can look in specific area of the sky, and basically Venus is not accessible and Mars is too bright. So it saturates. We tried, but it saturates. So I'm excited for this new telescope because at this wavelength of light, we're going to be able to do Mars. And it's going to have a window of observation where we're going to be able to do Venus. And so very quickly, I'm going to show you what we can do with this telescope, because I'm a planetary scientist. So this is what I would love to do with this telescope, not just astrophysics and galaxies and stars, which is interesting. But that's, this is what my interest is. And so what can we do? We can, for example, study the asteroids with an unprecedented resolution. With James Webb, we can already do that. We're going to do a different wavelength. And we discovered, for example, water in a main belt comet. But with this telescope, we can even further characterize small bodies. We can characterize small body also for planetary defense, for example. And we can have a very, very, very incredible spatial resolution. So we can have something like 4 kilometer per pixel resolution. So we can identify a lot of compositional features, for example, in these bodies. What we can do, for example, is studying the weather on Mars, because at this wavelength, for example, we can see the dust, we can see the clouds, we can see the water ice cloud, and basically combining together this very, very huge spatial resolution where we can see something like, for example, 4 to 10 kilometer on 1 pixel on Mars. Basically, we can investigate the evolution of the clouds. and how they move and how they evolve and how dust storms that are small and located in a specific area can evolve into massive global dust storm. And this is important also for future robotic and human exploration, for example. And we can explore the giant planets and the beautiful auroras. So this is a video, and those have been already explored very well with James Webb, but UV and this kind of wavelength allow you to explore in a different way the auroras and the connection with the magnetic field and how the sun, very high energetic particles are creating, so the sources of these auroras. So it's going to be incredible because with this very high resolution and even spectral resolution, we can get into the sources of the location of these auroras on the giant planet. And I want to conclude with one of my favorite topics, the ocean worlds, which are habitable environment, not around other stars, but in our own solar system somewhere else. And so these are moons or small, let's say, small moons around the giant planets, so around Jupiter, for example, or around Saturn. In this case here, we are probably looking at Europa. So around Jupiter, but Enceladus is another ocean world. It is a moon around Saturn, where under a crust of very thick ice, you may have an ocean of liquid water. And that water is sometimes mixed with some other organics, and you may have hydrothermal vents or some other sorts of energy. So you may have sort of habitable conditions. So those are environment in our own backyard where we can search for the ingredients of life and any habitable signature of life. And so here's an example of what Hubble could do with 2.4 meter primary mirror. And actually this was just re-examined, and people now they're saying that they're not even sure they saw these plumes on Europa. And what is on the right is a simulation of how HWO with this big mirror can act, and this very high resolution and spatial resolution, what it can achieve. So identifying the sources of these possible plumes in this habitable environment in our own solar system. So very exciting science coming, not just for astrophysics, but also for our own solar system, our own backyard, as I like to say. And so, and with this, I am concluding this journey into, the next flagship observatory. I hope you enjoyed it, and I'm very happy to get any question.